Most of this segment has to do with the various elements of the ANOVA table. So please keep reviewing this, understand all of those elements and how they relate to one another, and ultimately what goes into the final F test that gives us significance. So know that fraction, know the MS regression over MS residual, and all the factors that play into the sizes of those elements. Okay, so we'll start with the SS regression. And the SS regression gives us an indicator of how well we're predicting the DV. And remember specifically what this means is, are we predicting better than just saying the mean of the DV for any value of X, or the predictor? So remember that we would be doing a very poor job of predicting if we just said the mean of the DV for any value of the predictor. But that would be the best that we could do. Well, SS regression, we want to, basically that's the formula for that is saying, look, we want to improve on just having to do our best guess, which is the mean of the DV. So if SS regression could talk, it would say, am I doing better than the mean of Y? So that's what we see in the formula. We have, remember, the sum of the squared deviations between our predicted value of the DV and the mean of the DV. And the larger that is, the better, because that is going to comprise the numerator of our F test after we divide it by the numerator dF, or degrees of freedom. Remember, the numerator dF is k is equal to k, which is the number of predictors. And think about what happens as k would increase. So as k would increase, we would cut into our SS regression and thereby reducing the numerator of our F formula. And we don't want that. So what we don't want to have is a lot of predictors. We want to be parsimonious and judicious when choosing predictors, because each one uses up a degree of freedom. And so especially redundant predictors, predictors that are highly correlated with one another, we would want to eliminate those because we want the SS regression to be very healthy. The SS residual, on the other hand, we don't want that to be large. SS residual is an index of how poorly we're predicting the DV. So remember, it is the sum of the squared deviations between the observed value of the DV and the predicted value. And so we want that to be, those deviations to be as small as possible. Now, if we sum together the SS regression and the SS residual, we will get the total sum of squares. And remember, the total sum of squares is the observed value minus the mean value. Remember that. So the sum of the squared deviations, again, of the observed value minus the mean of Y, always the DV. So those formulas, if you need to review them, they were in the slides from last week. So I highly recommend knowing all of those and understanding conceptually what they're doing as well. Okay, so how do we get the MS regression? Well, we divide the SS regression by k. And so again, if we have a lot of k, we'll have a smaller MS regression. If we have a smaller number of k, we'll have a larger MS regression. And the goal is to have it larger. MS residual, we divide that by the denominator dF, and that is n, total number of points in our data points in our study, minus k, number of predictors, minus 1. So we divide SS residual by n minus k minus 1. And for that, we want lots of n, because we want to cut into that MS residual as much as possible, because that forms the denominator of our F test. So the smaller, the better. And remember, in our case of 620 n from last week, that's what happened, is we were able to cut into the MS residual a lot with that second big sample. Okay, so the SEE is the standard error of the estimate, and conceptually what that is the standard deviation of the distribution of residuals. We don't want that standard deviation to be large, because that means that we're not predicting well. We get the SEE by square rooting the MS residual, And we can also get it by the formula of the standard deviation of y multiplied by the square root of 1 minus r squared. So that's the way we can get the two ways we can get the SEE, which is kind of cool. So at the mean of a predictor, what is the predicted value of the dv? And that is the mean. So the predicted value of the dv is the mean at the mean of the predictor, and it's that way on any scatter plot. So you would go across on the x-axis to the mean of the predictor, wherever that is. You'd head upwards to the best fitting line, and then head across, and you'll always be at the mean of the dv. Finally, hopefully you know the answer to this by now. When there's no relationship between two variables, what is the expected value of the dv for any predictor value? And that is simply the mean of the dv.